All right, I'm Suren Byna from Lawrence Berkeley National Lab. I lead the ExalO project in the ECP portfolio. In that, we have two products. One is HDF5 and the other UniFi-FS. In the HDF5 project, we develop various new features that make HDF5 perform well on various new architectures and storage systems. And we also help a lot of applications in the ECP. So I may not be talking about every feature and application in this talk, but I will give a brief intro to many of them. So our team includes a lot of people from various organizations, LPL, Argonne, mostly LCF people, and HDF group is heavily involved in this. And we also have some subcontractors from North Carolina University working on GPUs. Okay, so this is a brief agenda for today's discussion. So I will be talking about a new feature called HDF5 virtual object layer. And a few of those virtual object layer connectors that we're developing to work on new systems. They also will give a very brief 1 or 2 slide introduction to subfiling and querying features that we're developing, and a few applications and benchmarks we are developing as part of this. So, as you might have seen, that performing I/O at a very highly optimized I/O requires a lot of tuning. And as these systems change, making HDF5 work for all these systems involves a lot of optimizing. But what we have been thinking about for the last almost 7 or 8 years we are developing this WAL framework is that if we can give the a level in the HDF5, just below the HDF5 API, one can take that API call and redirect those I/O operations with more advanced and optimized way. Let me see if you can, just in case if you want to see. Okay. So the WAL or virtual object layer framework is right below the API layer, and then one can take that and then do a lot of optimizations. And these new optimizations are called connectors, and these we have been developing a bunch of these connectors, as well as others who are not as part of the ExalO project, or the something that HDF5 team is not involved, are also developing a bunch of these connectors. So this is the high-level overview. The application typically calls the HDF5 API, and the operations are that are happening on the container level, which are more like a data set, the attributes, object, and various HDF5 objects. Those can be intercepted and done a lot of optimizations, and then go back to the actual storage. And all other HDF5 routines just use the HDF5 library infrastructure. So some of the connectors that that are available now are pass-through, which is more like a very basic template-like connector. Those just passes through, and then the two types of connectors in that are pass-through on terminal, and pass-through just intercept, do something, and then come back to the HDF5 level, which is more of a terminal level. And terminal has native and various other connections directly to the file system. So at the pass-through level, we have asynchronous, caching, data elevator, and provenance. Asynchronous is more like performing asynchronous I/O. Caching is to use node local and memory and storage to cache data. And we currently haven't been working on data elevator, but this was when there is a layer with a common namespace or file system between the source and destination file systems, we can use that more transparently and just to stage the data. And we also have provenance capturing connector that just collects the provenance. And terminals are native is the one that comes with HDF5, and there are DEOS, REST terminal connectors. And then we have recently been working on to work with Apache Arrow. The proactive data containers is another object abstraction that has a terminal mod connector as well. So in this talk, I will not cover all of them, but I will just go through the asynchronous and caching, which are most relevant. Okay. So some more information about Vault connectors. You can basically implement the callbacks for HDF5 data model operations. And as I already mentioned, pass-through, you can stack multiple of these pass-through connectors. And some of them are provenance tracking and asynchronous IO caching. So one can use asynchronous on top of caching, and then caching can go again on asynchronous IO. So it's more like multiple layers of these can be stacked and can be used. Terminal is our connectors are not stackable, and they are the final connectors because they are going directly to the file system, and there are various of these to work with cloud streaming. Some of them are non-HDF5 based files, such as RDS-BP, NetCDF Classic, and all those can be done with the terminal walls. And another one that I'm not going into the details here is the DEOS one, which is very actively developed. And and some of them are also dealing with S3 and Apache Arrow. Okay, just talking about the asynchronous wall, what it does is I think in Rob's presentation, he was showing about the defensive IO pattern where an application does checkpoints or stores the status and goes back to computation. So there are various phases of these computation and IO, computation IO, and it goes on. So if we can do this IO, which is right in this case, while the computation is going on using some additional compute resources, we can hide that IO latency completely. So that's what we have developed, and it uses an event set to manage the asynchronous operations. So basically, an event set is more like a bucket. You just throw all the operations, and then some other background thread comes and takes these things in the order they received, and then performs them in the background. So in that way, we can save the time for all those where computation can be overlapped, and the time savings would be like this. But we cannot hide the last time step or something that doesn't have a follow-up compute time to overlap it. And that's the time where we also do, if anything else is running behind these kind of things, they will be also done at that time. So we verified the performance with a couple of benchmarks that are in the AMREX application and the AMREX framework. And if we do normal baseline HDF5, it takes about 100 seconds to 200 to 300 seconds. But on the if we hide all of it, it would be pretty much only one time step time is observed. And similarly, this is for single level AMR and multi-level AMR plot files, and the 5 time steps examples. And we used the number, depending on the number of nodes, it scales pretty well. And yeah, I think that's basically that. And how to use it, this is a programming example. Without an async IO connector, you would be just using the HMI open, which is file open, group open, dataset open, and write the data multiple times if you have any multiple variables, and the other user code is there. If you're using the event set API, what you do is create an event set and use the H5 fopen underscore async calls. So all the fopen calls have a corresponding underscore async calls now, and those things will be using this event set to put the operation in, and basically all these are done. So the event set IDs have to be added here, and then the ES-wait is the call that makes sure any of the remaining operations have to be performed will be done at that time. Okay. So that's one basic approach, and this is we call this explicit asynchronous IO wall connector, where you have to use the event sets. There is also an implicit async IO version of it, where you don't have to change the code at all, but you have to specify that using an environment variable that you are using the async IO wall. So you have to, there is a command line option to set that, and basically you don't have to change the code, but you can just run that. But there are some control you would lose on when to run, when to issue these IO calls, but it still operates in most of the cases and gives good performance. Okay, so if you would like to give it a try, there is the source code is available here, docs are available here, and we have a bunch of future work that we are thinking about to optimize this further. One of them is when you have multiple IO operations that that can be merged to make a larger chunk of data to be written, then we can, we, in the background thread, can take two of these operations and then perform a single operation. But that is not there right now. And then right now we are also using a single background thread, not multiple of them. Basically, for each MPI process, there is one background thread we are using. And there is another work in progress called TaskWorks, which is a threading engine that has more flexibility than the current background thread we are using, which is the Argonne. Okay. All right.
Suren, before you go too much further, I got a couple of questions on Slack I thought it would be worth bringing up.
Go ahead.
Going back, way back, Stefan Wood had a question about the data elevator would allow stage data to be accessed by an analysis Sentinel program. So I guess the question is about the visibility of the data elevator data.
Yeah, so the with the data elevator, if the applications, all of them that are working together, let's say the data production application and consumption application, if they are launched at the same time, then the analysis application can probe where the file is and then use the staged file to read it. But if it is in a different program, completely separate, then the metadata about the staged file is not accessible and you cannot use it.
Great. And another question is about the asynchronous interface. Christopher Subich wanted to know, I guess to summarize, how common do you think it would be for platforms to make background progress in that async call, or will it be more common for all the I/O to happen in the wait call?
So there are, and with the applications we have seen, we can, and there is an assumption that applications can give us some memory to keep the data in memory. The next one I'm going to talk about in the cache wall, where we can use the node local storage to do that staging. So that would be much more practical. And another thing is that with the GPUs being used for most of the computation, and the CPUs and CPU compute and memory are not being used that much for any of the computation, we can use those resources for doing the asynchronous I/O. So I hope that answers the question.
On the same topic, how much CPU overhead do you think the background asynchronous I/O would take up? Would it?
Yeah, we did measure the CPU overhead, which isn't that much considering the hiding the entire I/O latency for most of the time steps. So if just purely there is no time between compute and I/O at all, or basically there is no compute time, and you have a bunch of these coming in, we see about 10% in a max case, but that is just for the creating the background threads and maintaining the background threads. But when there is overlap, that is not a major issue. Another argument is there that because this asynchronous I/O is also adding communication, that communication overhead may be interfering with the computations phases communication, and how much it is slowing down that thing. We haven't done that study yet. So there is a possible hit in that we may be slowing down the computation phase when we are competing with that, and probably we had to come up with a proper or intelligent way to avoid that.
Great. And then real quick question about this results, the scalability results that you showed. Are they weak scaling or strong scaling?
Let me see. These are strong scaling, 385 gigabytes of data, and that is per time step. So as you have more time steps, that much data would increase. But with the number of nodes, it is not increasing, or number of cores.
All right. You've listed quite a bunch of activity on the Slack, so proceed, and I'll let you know when there's more questions.
Okay. All right. Okay. Cool. Okay. All right. So the other one is in many of the systems that are coming up, so like PETA GPU Summit, and the Frontier, and the follow-up Aurora, everybody is going to have this node local storage. And there was a paper on I/O 2020 or Storage 2020 by Glenn Lockwood that discussed about there may be more layers, and sometimes the layers may be hidden, but the fact is there are going to be multiple layers and multiple heterogeneous layers. So how do we take advantage of those layers using the caching approach? So we came up with this. This is mainly developed by Huhyo and Venkat at ILCF. So the caching and staging data for fast scalable I/O, and data migration to and from the remote storage is performed in the background. So basically, we did an implementation where we can where we did the entire implementation using cache wall, but then we kind of made it, since some of the asynchronous operations are already done by the async IO, we are now stacking these connectors where asynchronous IO stacks on cache and another that stacks on another async IO. So this work is still ongoing, but all the complexity is hidden from the users in using those layers. So this is one example of it. So compute and IO phase. In the IO phase, instead of doing moving the data from RAM to parallel file systems, you'd be moving that to a node local storage, which is faster. So that is the time we are going to save. And if we do that asynchronously, asynchronous movement here, then that is what we are seeing as benefit. So we initially tried moving the data from memory to the node local system using memory map files, and asynchronously calling the data set write function from moving the data from there to the file system. When it is reading, so we are using the MPI window options for one-sided remote accesses, so that even the data is on different nodes, we can still access that as if it is in the same location. So more optimizations are being done for one-sided communication for accessing the remote node storage. So that is an ongoing activity. So initial study with a parallel write performance using a simple benchmark so this is showing the gigabytes per second performance on theta. So without caching, Lustre performs about half, very small actually. And then when we go for SSD-based caching, we get slightly better performance. And then if we use RAM as caching, we get much better performance, which is pretty close to the peak of that performance. And when we go beyond 32 nodes, the increase with the using SSDs is even more, where the Lustre performance kind of plateaus there. And similarly, read performance is also increasing beyond 32 nodes much faster. All right, so I gave a very brief introduction to them, but if you have more questions, let us know. And the wall connector development, if you are interested in developing new walls or something, there please subscribe to HDF5 wall subscriber group. And then the simple template wall connector you can take for your development would be the external pass-through. And then from there, you can do the external pass-through is basically all the wall callbacks are implemented as transparent no-ops, and then just invoking the underlying wall connector, which is native. And then if you want to do more optimization or add new things to that, build with the logging enabled and follow the instructions that are given and modify for your purposes. Okay, so that's about wall. Any questions that I should answer now, or no on?
We have a question about memory allocation, but Scott fielded it on slide. I think we can press on. You got a few minutes before.
Okay.
All right.
Yeah, I'm late behind. So let's subfiling, which is a compromise between file per process and single shared file. So we can store, HDF5 has been storing the data as a single shared file for a long time, but it has various issues with the locking on the file system and all this. So now we are developing a new subfiling feature that allows, instead of creating either file per process or a single shared file, it would be somewhere in between, and the user can specify configure all those options. Okay, and the initial performance shows significant benefit as expected on Summit. And there is another feature called querying the data sets and metadata. So we have added a bunch of new APIs to HDF5 to query data, create a query, and then do a combination of those queries on various conditions and apply them in flows. And to make them faster, one can use the indexing approaches, which are based on fastbet and various other types of indexes. So these also show very scalable performance as we increase the number of MPI processes for indexing and building the indexes and evaluating the queries. So in the interest of time, I may not be going into the details of this, but we do help a lot of applications, and one of them is the earthquake simulation application. So they were previously using a lot of the ASCII and binary-based file formats. So we moved them completely to new HDF5 integrated and HDF5 files. And they do perform very well. For example, the S file, which is half in size and 3 times faster in accessing. And similarly, some of these are much faster. And the subsurface output, we apply the CFP compression and achieve very good performance as well as the compression. Okay, and as I already mentioned, the AMR-EX is a framework for AMR, and it has various use cases. And some of the use cases are the NICS use case, which does the XSky, the universe simulation, and using the asynchronous explicit, we get pretty good performance there. So using this one, and then similarly, Castro is another simulation that has a similar use case, and IO pattern gets good performance there too. And to make HDF5 and test well on the system, so we came up with a new benchmark suite called H5 Bench. If anybody is interested, it has various features, including the IO patterns seen in many of the ECP applications, and then it supports asynchronous and asynchronous. We also have CPU and GPU IO modes, and the collective buffering on/off, and the file system configuration, such as striping and alignment, can be tuned as configurable options. Okay, all right, I will stop there. So there is a lot of work going on, and then if you have any questions, call help desk at HDF Group is typically available, and a lot of resources, as Scott mentioning. And if you have any questions, then call there, and a bunch of useful links and info here. All right, I'll stop there.